So by now you should have equations of lines in three-dimensional space locked down. So we're going to look now at how to write the equation of a plane. Okay, so what we're going to see is that a plane, the equation of a plane, is going to be determined by a single point that we know lies on the plane and something called a normal vector. So if you're curious how mathematicians decided to define the word normal, what it means here is that a vector is normal to a plane if it is perpendicular to every vector within the plane. And we know that to be perpendicular to every vector within a plane, its dot product with all of those vectors must be 0. So this gives us a geometric description of the plane, and it's also going to help us derive an algebraic formula for that plane. So the point-normal form for the equation of a plane is going to be some vector n, that's our vector that's normal to the plane, times the quantity r minus r naught equals 0. R is just going to represent the three quantities x, y, and z that are the variables in our equation, and r naught is going to be the given point x naught, y naught, z naught. We can expand that out into a slightly more useful form that looks like a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where x naught, y naught, z naught, again, is our point, and a, b, and c are the components of our normal vector. The distributive property and a little bit of basic algebra would then allow us to rearrange that into what's called the standard form of a plane, which looks like a times x plus b times y plus z, c times z is equal to d. A, b, and c are still the components of our normal vector, but notice that we can no longer pick out what our x naught, y naught, and z naught are in this form. We can interpret each of these algebraic equations geometrically by remembering that the normal vector ABC is going to be perpendicular to our plane. Every vector in the plane has to be orthogonal to that normal vector. And we can check that condition by looking at dot products. The dot product of any vector within the plane and the normal vector must be 0. All right, for our first example, we want to write the equation of a plane that goes through these 3 points. Now, we've been saying over and over that in order to write the equation of a plane, we need a vector, a normal vector, perpendicular to the plane, and a point. Well, we've got an excess of points and absolutely no vectors. However, we do know some vectors that lie in the plane. Let's let u be the vector that connects this point, P. We'll call these P, Q, and R. So let's let u be the vector that connects P to Q. Since P and Q are in the plane, the vector that connects them must be. So that's going to be the vector 1, 3, negative 4. Similarly, let's let V be the vector, we'll do P times R, or PR, not P times R. And that's going to be the vector 2, 0, negative 3. So we have 2 vectors that lie in the plane. We want one that is perpendicular to them. Well, guess what? U cross V is perpendicular or normal or orthogonal. They all kind of mean the same thing, perpendicular to both U and V. And therefore, it can be our normal vector. So let's calculate U cross V. So we're going to do our determinant here. We have 1, 3, negative 4, 2, 0, negative 3. And so let's see, we get negative 9 minus 0 times I minus negative 3 minus negative 8, so plus 8 times j plus 0 minus 6 times k. So that's the vector negative 9i, not minus I, negative 9 times I, minus, we get minus 5j minus 6k. So our normal vector, n, is going to be the vector negative 9, negative 5, negative 6. Now we just pick any one of our points. So I'm going to use P as my point. So remember our equation looks like A times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where a, b, and c come up from our vector. So this is going to be negative 9 times x minus 1 plus negative 5 times y minus 2 plus negative 6, which of course I can write as minus 6 if I want, negative 6 times z minus 3. That's our expanded form. If we want to write that in the standard form, we can multiply everything out. So we get negative 9x plus 9 minus 5y plus 10 minus 6z plus 18 equals 0. So let me just highlight right now. This is our expanded form. And we're aiming towards our standard form. Our standard form is going to look like, let's say, negative 9x minus 5y minus 6z. So again, remember, that's got to have our a, b, and c into it. It's just d that's going to capture all of the information that comes from our particular point. And we have 9, 19. 19 plus 18 is 37, so we're going to get negative 37. And then we can do a quick check. I'll do it over here. I'm just going to pick one of the other points, q. I'm going to plug q in there. So negative 9 times 2 minus 5 times 5 minus 6 times negative 1 gives me negative 18 minus 25 plus 6, which is negative 12, that's negative 37. Look at that. So it did in fact check with point Q, so we can be assured that we have also found the correct standard form of our equation. Now notice that this equation, the expanded one, would be different depending on which point we chose. We would get a different expanded form if we used point Q or point R, but this equation, the standard one, it would be the same regardless of whether we started with Q or R. All right, in our next one, we are looking for a plane that contains the point 0, 1, negative 1. And we know that the plane is perpendicular to the line r of t equals 1 plus 2t, negative 3 plus t, and 4 minus 2t. So we know that this line has a direction vector 2, 1, negative 2. And that's coming from, it's a very weird little symbol I just drew. Whoops. That is coming from the equation. I'm taking the coefficients of t there to get my direction vector from the line. Well, if the line is perpendicular to the plane, then this must also be perpendicular to the plane. Or normal. Wow, I really spelled that very badly. Perpendicular. There we go. So this is normal to the plane. So now we have our normal vector. We can use any multiple of this if we wanted to. If we wanted to use 4 to negative 4, we could multiply everything by 2. We could divide everything by 2 and use 1, 1/2, negative 1. We can't use 0 as a multiple, but that's the only one that's off limits. I'm just going to go ahead and use it in its form. So I'm going to write my vector, again, using the a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. We're going to get 2 times x minus 0 plus 1 times y minus 1 minus 2 times z plus 1 because of the negative equals 0. So there's our expanded form. And that one is going to, well, we only have one point here. So now if we write this in the standard form, we get 2x plus y minus 1 minus 2z minus 2 equals 0, which gives us 2x plus y minus 2z is equal to 3. And notice that if we had chosen a different vector, if we had chosen to use, say, the vector, let's say 4, 2, -4 as our normal vector, the only difference would be our equation, everything in the equation would have gotten multiplied by 2. So this would have led to the equation 4x plus 2y minus 4z. And then our d value would have ended up being 6 if we had chosen a different vector. These two equations are in fact equivalent to each other, meaning that any point that lies on one that satisfies one of them is going to satisfy the other. All right, in this example, we're asked to determine whether or not a particular line intersects the plane. And so what that would mean is that for some value of t, a point on the line is also a point in the plane. So all of the points on the line are represented in this form. So what we can do is we can plug that into our equation. So I'm going to replace x with 2t, and I'm going to replace y with 1 minus t, and I'm going to replace z with 3 plus 4t, and I'm going to set that equal to 5. And if this equation has a solution, then we will know that the point and the plane and the line do intersect. So we get 4t minus 1 plus t plus 9 plus 12t equals 5. Combining t's, we have what? 17t. And that's equal to 5 minus 8, which is -3. So we see that when t is -3/17, that point is going to lie on the plane. So they do intersect. If they didn't, we would have ended up with no solution to our equation. Now we need to figure out where they intersect. Well, they're going to intersect at the point 2 times -3/17, 1 minus 3/17, or 1 minus -3/17, which becomes 1 plus 3/17, and then 3 plus 4 times -3/17. And so if we tidy that number up, we get, so this is our point of intersection. P is going to be the point -6/17, 20/17, and then 3 becomes what? 51/17 minus 12/17, so that's 51/39/17. All right, our last example is going to tie together a whole bunch of ideas that we've been working with. First of all, let's just start by identifying the fact that I do know how to spell the word and. So we're going to rewrite that as A-N-D. All right, and with that goof out of the way, hopefully we can get through this problem without any more goofs. So we want to find an equation for the line where the planes, these two planes, intersect each other. So the first thing we might want to do is confirm that the planes are not parallel. So if we look at their normal vectors, I'm going to denote the normal vector for q as n sub q. That's going to be the vector 1, 2, minus 1. So we get the normal vector by plugging out the coordinates of each of the variables. And similarly, n sub r is going to be 1, 1, 1. Since those are not multiples of each other, that means that our planes are not parallel, which must mean that they intersect. So in three-dimensional space, if planes aren't parallel, then they have to cross each other, sort of like what lines do in two-dimensional space. So now that we know that they're parallel, we know that they're not parallel, we can proceed. Now, we need two pieces of information in order to write the equation of a line. We need a vector, and we need a point. And so we're going to find each of those separately. Now, the vector must be perpendicular to NQ and NR. If that vector lies inside of the plane, then it's perpendicular to both of the normal vectors, which means that one vector that would work is NQ times NR. That's going to work as our direction vector. Okay, so let's compute that. So when we do that, we're going to get 1 minus 2. Did I do that right? Yes. We're going to get, 2 minus negative 1 times I minus 1 minus negative 1 times j plus 1 minus 2 times k, which means that our cross product vector is 3, negative 2, negative 1, and that is going to serve as our direction vector. Now we need a point, so let me move over here a little bit to get our point. To get the point, what we can do is we can pick an x value, or we can pick any value for one of our coordinates. And once we've done that, we'll solve for the other two on each plane. So let's let x be 0. We're going to let x be 0. No, let's let x be 1. Normally I would choose x equals 0, but I have some insider information on this problem. So I'm going to let x be 1. And so when I do that on plane Q, I'm going to now have 1 plus 2y minus z equals 1, which is equivalent to saying that 2y minus z is 0. And on plane R, I'm going to have 1 plus y plus z equals 1, which gives me that y plus z equals 0. So now I have two equations in two variables. I have 2y minus z equals 0 and y plus z equals 0. I can use elimination to get that 3y equals 0. So that y is 0. And then putting that together with this guy right here, I now know that z is equal to 0. So what I have just discovered is that the point x equals 1, y equals 0, z equals 0 is on both planes. So now I have the two pieces of information I need. I have a point, and I have the direction vector for my line. So my line must be the line 1 plus 3t, 0 minus 2t, 0 minus 1t, which of course I can write as 1 plus 3t, negative 2t, negative t. All right, so what we've learned is that if we have a point, x naught, y naught, z naught, on a plane, and we have some vector ABC that's perpendicular to the plane, then we can use that information to write equations for the plane, the expanded form, and the standard form are here to peruse one final time. Up ahead, we have one more application of the cross product. We're going to use it in order to calculate the distance from a point to a line.